All right, go ahead.
And we are back. Good to see you. Hope you're doing well. This is chapter 14, the first part, meant for April 1st, April Fool's Day. Sorry though, I'm not playing a joke on you today. This is real stuff, meant for Wednesday, April 1st. And also quiz 8 is due tonight, so make sure you upload that and get that on Learning Suite. Yes, we'll go through the outline first of chapter 14, but first let's do a little review here of chapter 12 reactions and see if you can get the correct products. You can pause it at this point and try to go through it and see if your answers correspond to mine. And I'll point out a few things here. Remember, chapter 12, we've got the reduction reactions, mainly with alkenes, and we've also got the oxidation of alkenes and the oxidation of alcohols. So it's a big set of new reactions. It's about, I think, what we count them up, 8 new reactions. So good, let's unpause there and look at this first one. What type of alcohol is this? First thing to look at, well, it's primary. And this first reaction with chromic acid will go to the carboxylic acid. Now we can combine this a little bit with chapter 13, IR data. So if we look at the IR, the infrared spectrum of an alcohol, we'll see a very broad stretch at 3,300, remember inverse centimeters in the IR. That will tell us it's an alcohol, but we don't have a carbonyl here with the alcohol. But when we do the oxidation to the carboxylic acid, we'll add that 1,700 peak also. So you can kind of follow that reaction by IR there. But yeah, you should go all the way to the carboxylic acid with the strong oxidant. If we use PCC, pyridinium chlorochromate, we'll stop at the aldehyde. And notice here, we'll just have the 1,700 peak, not the 1,700 and the OH peak. This one will have 1,700 and the 3,300. This will just have the 1,700. So we'll see this 3,300 in the case of PCC go away to, again, the aldehyde product from the primary alcohol. Okay, reduction reaction. If we have hydrogen palladium with an alkene, we'll go to the alkane. And if we have an alkyne, and if we do hydrogenation with XSO, we would go to what? We'd go to pentane all the way to the alkane. But if we do the reduction with sodium and ammonia, what do we get here? We get the trans double bond. So we'll get this 2-pentene, E2-pentene, the trans double bond from the reducing agent, which is a sodium metal. Remember, it has that electron here, and actually you need excess or 2 equivalents. You don't need to draw that there. This is implied to be excess of these reagents, and it stops at the trans double bond. All right, let's look at palladium Lindlar. That's the poison catalyst with an alkyne. Your product there should be what? The cis alkene. Okay, that's the half reduction or the poisoned Lindlar reduction, and it just stops at the cis alkene. Okay, let's take that same product here and now oxidize it with MCPBA. That stands for what? Metachloroperbenzoic acid, and we'll get the cis epoxide there. These are stereocenters, so it will be a DL pair. It can either be up or down, but the ethyl and the methyls here are cis to each other on the 3-membered ring. Okay, what's this? O3, ozone, and then separate operation we quench with dimethyl sulfide with this alkene here. Remember, ozone's molecular scissors. You chop both the pi bond and the sigma bond apart, and we get out the cyclohexanone product, the ketone. The other carbon here ends up as formaldehyde. We don't generally worry about that because it's water soluble and it's a very small molecule. Usually the bigger one is the important one we're interested there. In that case, if we have an alkyne with ozone, remember that will go all the way to the carboxylic acid. And in this case, it's symmetric, the 2 methyls there. the carbons of the alkyne get oxidized to carboxylic acid, so it actually generates 2 of those. If you leave that 2 out, don't worry, you'll still get full credit one like that. All right, the last one, LAH. Got to remember what that stands for. Another reducing agent is one of those hydride reducing agents, lithium aluminum hydride. And that's a nucleophilic hydride, hydrogen with its pair of electrons, draw out that structure. Again, remember what that is. It can actually displace alkyl halides or leaving groups and give what? The alkane product. So hopefully you did okay with that. Look back through the chapter, back through your notes, rewatch those chapter 12 videos, and you should be okay with these basic type of reactions. All right, let's go to the main event today, which is chapter 14, NMR. And this stands for what? Nuclear magnetic resonance spectroscopy. And that's quite a mouthful. Nuclear, is this fission or fusion? Are we talking about nuclear bombs here? No, that's very high energy events where we change the composition of the nuclei of a heavy metal, plutonium, uranium, things like that. We're actually, ironically, talking about the lowest possible energy event using radio wave frequencies, which is, again, very long wavelength electromagnetic radiation. And this is in the 10 to the minus 6 kcal per mole range energy-wise, because, again, the wavelength is very long there. And what does this mean then? Let's look through the outline here of the chapter. We're mainly looking at proton and C13 NMR. That's the heavier isotope, the less abundant one. These are the NMR active nuclei, important for organic chemistry. We're talking about nuclear spins here. We're not talking about fusion or fission. So like I said, this is very low energy effect. B naught refers to a large external magnetic field. So that's the magnetic part of the name here. You've played around with magnets here, little, refrigerator magnets. They're very weak. But we're talking about very large external magnets here that create this resonance effect where the spins of the nuclei can either line up with the magnetic field or against it. And then we're going to use radio frequencies to take those spins out of equilibrium with the magnet. We'll go over a little bit of the physics. You need to just know the very basics of it. The interpretation of it is the important thing. The radio frequency pulse here is important. The specific frequency corresponds to the strength of the magnet. I'll show you that. The strength of the magnet is very large, many Gauss, thousands of Gauss. I'll do a little bit on the units of magnets, or Teslas. Maybe you've heard of Nikola Tesla, the famous physicist, and the units for that. But megahertz is the frequency of the radio frequency pulse here. The units for NMR is ppm, or parts per billion, out of the frequency units compared to the frequency of the magnet. And the range is 1 to 10 ppm for proton NMR. And it's relative to TMS, which is tetramethylsilane. That's an internal standard that we always reference and put at 0 ppm frequency for the units. And then the other signals that we see from the molecule are the shift. And these signals come from non-equivalent sets of protons. We'll have to define, what we mean by non-equivalent sets. Those are the different types, numbers of signals that we can see from the sample. We'll integrate that, see how many protons are within that signal, and then we'll look at the splitting for how many neighbors they have. So those are 3 concepts. I'll go to the chalkboard and review those 3 elements of NMR that you need to keep track of there. But yeah, the signals, the sets of equivalent hydrogens, are magnetically non-equivalent, so they show up at different spots within the ppm spectrum. They can either be homotopic and antiotopic, or diastereotopic. We'll talk about topicity a little bit, and symmetry, and then we'll do a lot of examples to get to the idea of how many signals we expect to see in a molecule. So the shift value, non-equivalent sets have distinct shift values, or delta values, depending on whether they're shielded or de-shielded. If they're shielded, they're surrounded by more alkyl groups, and the signal for that proton is shifted upfield, we say. If it's next door to electronegative groups or on a carbon that's hybridized, highly hybridized, it'll be deshielded and shifted downfield. Here's the range here, 10 to 0. We'll look at the types of hydrogens. You won't need to memorize this thing. In fact, I'll put this whole shift figure here as part of your data sheet for test 4. But you'll do enough problems so you get familiar with this. Alkyl hydrogens down here. If it's alpha to a heteroatom, like a halogen or an alcohol, it's shifted down here to 3 or 4. If it's vinyl, sp2 hybridized carbon with that hydrogen, it's 5 or 6. If it's aromatic, it's down here. And if it's on an aldehyde, it's way up here at 9. So they spread out here. Alpha to a carbonyl, that's not right next door to this. Well, yeah, it is, but it's different. It's not on the same carbon bearing that, it's the next carbon over. So it's not shifted as far downfield. And if it's benzylic or next door to an aromatic, not right on the benzene group, it's also in this range right here. So there's some overlapping regions that are kind of ambiguous that way. Let's finish out the rest of the thing. Wow, it looks like a lot of details we got to keep track of. But these are the effects of what affects the shift here, hybridization, as well as proximity to electronegative groups. Integration just counts up the number of hydrogens in that non-equivalent set, proportional to the area under the signal. It's actually a separate experiment that takes the derivative of that curve and calculates the area under that signal. And that's proportional to the number of hydrogens within that set. Splitting, this is a very powerful thing. The J value in Hertz is the so-called n+1 pattern. That gives you the multiplicity. N is the number of non-equivalent neighbors. So the N means neighbors here. If you have one neighbor, that's 1 + 1. The multiplicity for that signal shows up as a doublet. If you have no neighbors on the adjacent carbons, no adjacent hydrogens, it'll show up as a singlet. The n+1 value will be 1. But that can also be 3 or 4. You can have triplets or quartets. And this is because of the fact that those non-equivalent sets next door, the neighbors, actually can add or subtract to the incident magnetic field. They add or subtract to the external magnetic field and create this splitting pattern, we say. It's very powerful to figure that out. We can have multiple J systems that can have multiple non-equivalent sets, and this formula helps keep track of it. But we'll just do it qualitatively, and you'll see that can make the complexity of the signals greatly increase. Alkene splitting, for example, whether the hydrogens are geminal, that's a J1, J2 relationship. If they're cis or trans to each other, that's a J3 thing, and you can tell cis or trans depending on the magnitude of that J value. So we'll do a little bit on that, not much, but we'll show you the basics of the complexity there. Some of the details here involve proton exchangeable groups like alcohols and amines. They exchange rapidly, so technically we don't see any splitting typically to those. So they'll just show up as broad singlets. Why is that? Well, hydrogen bonding. Okay, so it's a consequence of the property of those functional groups. Structure determination. So we're going to be like Sherlock Holmes here, combining this with mass spec and IR information to figure out what the structure of the molecule must be given the data. Okay, the proton C13 data along with the IR and the mass spec. It's a very powerful combination. So we'll do some structure determination of simple compounds, and we'll propose a structure, and we'll recheck to make sure things are internally consistent there. We'll work enough problems together. Yes, you can also do C13 NMR. It's only 1.1% abundant, so it's less sensitivity, but it has a very wide ppm range, very diverse range here. We normally run it in decoupled proton modes, so they just show up as simple singlets and non-equivalent sets. This relates to the symmetry of the molecule. There's such thing as two-dimensional NMR, two-dimensional correlation spectroscopy, or COSY it's called, or het-core to other atoms besides hydrogen. And then you can take 2D slices through these images using proton and P31 NMR to get a computer-generated image that we call MRI, for magnetic resonance imaging in the clinic. So some of you have probably had an MRI or seen it done. Very, large, expensive machines, but you can image especially the soft tissue within bodies, and you can get an idea of data complementary to X-ray information or CAT scan information, which is more the harder bone and collagen tissues of the body. Anyway, okay, so that's the basics of the outline. Things we're going to be going over. Let's go back to the board here and look at the fundamentals we're talking about. What are the 3 things we need to get out of NMR? So we're not going heavily into the physics and the math of NMR. The main thing for us is the organic structure determination. So the key idea here is the shift. By the shift, we mean the delta value or the ppm value. That tells us what? The kind of hydrogens. Okay. And it can be multiple in a non-equivalent set, but based on the shift, where it is in that range from 0 to 10, we know the kinds of hydrogens that are in the molecule. They're not all equivalent. NMR is able to differentiate between those different types or kinds of hydrogens within these non-equivalent sets, we call them. Okay? Now, that's the shift. Okay? The other key idea to keep track of is the integration. And the integration tells us the number in each set. Okay? So that's different than this. This is the kind of hydrogens in the sense. This is how many are in each set. And that's a separate experiment actually integrating the area under the curve for that given signal. But that's very powerful to know what types or kinds of hydrogens we have in a molecule and how many are in each position. So a methyl, for example, has 3 hydrogens, whereas a methylene only has 2 hydrogens, right? Or a methine 1. Okay, so we can tell a lot about a molecule just looking at that. But then we combine this with the splitting, and the splitting tells us the J value or the coupling, and that tells us the number of neighbors. Okay? And the number of neighbors goes into this little simple formula. Number of neighbors plus 1 gives us the multiplicity. And that multiplicity can either be a singlet, doublet, triplet, or quartet, or quintet on up, depending on how many neighbors it has. So yeah, this tells us then what? The number of neighbors. The kinds here, the integration of the number of neighbors. Very powerful. We can put that together in a qualitative sense and learn a lot about molecules. So those are the 3 things, key-wise, that you really need to keep a focus on. Today we're mainly talking about shifts. So we'll show you a little bit about integration and splitting, but the whole picture will come, I think, in the second class period. All right, let's look at a little bit on the physics now of NMR and what we mean here, because this is kind of a strange phenomenon, I think. So we got a nucleus, the heavy part of an atom, right? The interior, where the protons and the neutrons are. So yeah, it's just a ball of those dense subatomic particles, the nucleus. Well, the nucleus can actually precess or spin, okay? And the spinning here creates a angular momentum. And we can actually measure this angular momentum as a little mini magnet, or mu bar, we call it. So this spinning or precessing of the nucleus creates this little magnetic effect, okay? So it's different than an electron spin, although it is similar to an electron spinning. It's a quantized effect also. But here we're talking about the nucleus. And this spin has directionality to it. So as that nuclei spins, it precesses. And the spin, we say, has to be of a quantum mechanical number of 1/2 or -1/2, something besides 0, okay? It turns out that most of the nuclei that have an odd number of total protons and neutrons are NMR active. If it's an even number of that sum, it's probably not NMR active, although there are some that have an even sum that's still NMR active. So it gets into a lot of the physics of it. Now, the sample here, and there's a lot of nuclei in our organic sample, is placed in a magnet, the spectrometer, the NMR magnet, which will have this value for the magnet, the external magnet, of B naught. Sorry, that's the physics symbol for a magnet, B naught. Don't worry about that. But that surrounds, in the spectrometer, this big magnet, and it is quite large. A typical magnet used in NMR can be 14 or so Tesla. And a Tesla equals 10,000 Gauss. Okay. 1 Tesla is 10,000 Gauss, and maybe you've heard about Gauss and Tesla, famous physicist, whatever. But yeah, how does this really relate to what we've experienced with magnets? Well, you've all played with the little mini magnets, right? Refrigerator magnet. 1 refrigerator magnet is equal to about 50 Gauss. Okay. And that's how many Maxwells per square centimeter. So it is a force thing, a force at a distance, kind of a magical effect, right? Those are ferromagnetic materials that have permanent magnets associated with them. Here we're talking about molecules, right, that have this ability to respond to this magnetic field, but we're only looking at the spins associated with them, okay? And this turns out to be an effect, even though it's a super huge magnet here, the spin effect of this alignment in this large external magnetic field, some of the spins within the nuclei of the sample line up with the magnetic field, okay? They respond at a distance within the sample. We're not destroying the sample like mass spec. It just stays in the spectrometer. It's actually in a tube, okay? We'll talk about this. This is in the probe region inside the thing, and I'll show you a schematic of the actual spectrometer. What happens here is we apply a RF pulse, radio frequency pulse, and this corresponds to changing the spin states of the nuclei from aligned with the magnet to disaligned with the magnet. Okay, so it's back to the same spectroscopy idea, where we have a ground state for the spins, and then we have a state up here where the spins are not aligned the same way. So this is not exciting an electron, this is changing the spin state of the nuclei, if you can wrap your mind around that. So this RF pulse is what actually excites or changes the spin state, and then it decays back down at some given time. Okay, and you know, those times and everything, I'm not going to go into that. But this RF pulse, we say, changes the spin, so this is in your nucleus spin, which is now out of resonance of the magnet. So initially, the spins are aligned with the external magnetic field. We call that they're in resonance. Okay? We're not talking about delocalizing electrons in pi systems or lone pairs here. We're talking about the spins of the nuclei lined up with the magnetic field. The RF pulse then puts them out of the resonance. There's a frequency associated with that. It turns out to be super, well, the frequency here can be variable. It can be 600 megahertz. And that's in the radio frequency range, but that corresponds energy-wise to only about 10 to the minus 6 kcals per mole. So that's an extremely small amount of energy. We're not ionizing thing or breaking down the nuclei. We're just changing the orientation of the nuclear spin out of resonance with the field there. There's a formula associated with this frequency nu. It corresponds to gamma, which is the gyromagnetic ratio for a given atom, times the field strength of the external magnetic field divided by 2 pi. That's the basic NMR formula, which says that the frequency needed for the RF pulse is directly proportional to the magnitude of the magnetic field. So in the old days, the frequency here was about 60 megahertz, and the strength of the magnet here for that was about 1.4 Tesla. Okay? That's a lot of Gauss, very strong. Nowadays, 600 megahertz is typical, and that corresponds to a magnet of 14 Tesla, you can see there. Okay, let's look at the practical thing. What are the units here? So we've got frequency here, and we've got magnet strength here. We've got our little diagram. Let's make some room here and figure out from a practical sense what we're talking about. It's this delta value, okay? And delta is equal to the position of the sample, okay, whatever proton we're looking at, minus the position in frequency numbers of TMS. TMS stands for tetramethylsilane, okay? And most things have a higher frequency relative to TMS. This is highly electron rich and it's highly shielded, so it's always to the right. We're going to give that arbitrarily 0 frequency unit. But this is over the spectra frequency of the machine. So it depends on how strong of a magnet you have. Like I said, the old days was 60 megahertz. Nowadays we have 600 megahertz or 500 megahertz machines. And so this turns out to be, in a practical sense, for chloroform. So the first molecule we'll look at, there's the proton we're observing here. The position of this at 60 megahertz is 437 hertz minus 0 hertz. Again, this is the frequency, right? The new value for the RF pulse over the hertz of the magnet, which is 60 times 10 to the 6th hertz. Okay, and that comes out to be the new unit, 7.28 ppm. So wait a minute, how do you go from hertz to ppm? What does ppm stand for? Well, that's another representation of the delta value, okay? And ppm, you know from other definitions, parts per million. Parts per million of what? Hertz values for the signal, okay, that we're observing, and then the hertz value for the instrument. This is 10 to the 6th, or megahertz. So that's parts per million hertz numbers out of a million hertz, okay? So that's what the term delta or ppm means. You'll see these used interchangeably, okay? Notice that's within the 0 to 10 window. That's way up there, a de-shielded value of 7.28. Okay, yeah, let's see. So we've defined that ppm value. Let's look at the real thing here. Let's go back up and look at the practical information, the stuff you need to know, really. It's enough on the physics of it. So here's an actual large NMR device here. This big barrel here looks like a big washing machine, you could say here. This has the large magnet inside. It's a superconducting magnet. These are coils of niobium, chromium wires that are in 2 cooled cryogenic jackets. These are these ports up here that allow the liquid helium and liquid nitrogen to escape. These magnets are very precisely made and very expensive, by the way. Inside, right in the center here, this is where the sample goes in, and inside we say this is the probe region. This is where all the electronics are. Both the RF frequency pulse generator and the detector are wrapped around this sample position here. And so in the console here, we have the radio frequency generator and the electronics for the detector. So even though these are very low energy events, they have to be very precisely made to get the right signal to come out here. So this is processed via the computer, and then we see the NMR spectrum for the sample as it goes in there, if everything goes well. So let's look at it for chloroform. So here's our first signal. I include a lot of data on this, and this is for the old 60 megahertz machine here, and I'm plotting the delta values down here in the X region. In the Y region, we have absorbance, okay? So you can picture that these frequencies are being swept, just like we talked about with spectrometers in general. So we're going from 600 hertz here down to 0 hertz. And when we get right here at what, 437 from our calculation, we see this absorbance. Okay, there it is, 437. Okay, and then it comes back down. And it's kind of noisy here. If you run a lot of signal here, you can get that to go away. And there's one other little peak way over here at 0, and what's that for? TMS, which is added to the sample, tetramethylsilane, and we can fix the 0 point there, 0 delta or 0 ppm, right at that point for formaldehyde. So good. That's the basics of how it looks like. Yeah, let's go back to the board here, and I'll give you a little bit on the history of this. So chloroform, that's kind of boring, just one signal. NMR was developed during the 1940s and 50s. What else was happening then? Well, you had the Manhattan Project, where they were developing what? The nuclear bomb. And that's where most of the interest and money went, by the way. But there were two physicists, Purcell and Bloch, who were interested in the fundamentals of nuclear science. And the one issue was the spin states of the nuclei. And at first people thought, well, who really cares? That's very low energy. But they persisted and kept at it. And they built some devices. You know, they had to have the magnetic field, so they had large iron core magnets, and they had, you know, RF generators, and they could see the absorbance for the corresponding to the nuclear spins, and they thought that was great. And so they built a device finally, and they said, okay, let's get a real molecule here that has some NMR active things. So they were doing proton NMR. They got kind of bored with metals. They said, let's do something with hydrogen in it. And they sent a grad student over to the chemistry department stockroom. Remember, these are physicists. And they said, well, get a sample that has some hydrogen in it. So the grad student walks into the stockroom in the chem department and says, oh, I need something with hydrogen in it. How about hydrogen gas? You got some hydrogen? Well, that'll be a little hard to put in your NMR tube. It's a gas, after all. Well, what else do you have that has hydrogen in it? Well, we got some ethanol. Okay. So yeah, this was a Harvard graduate student, so he was familiar with ethanol. So he said, yeah, give me the ethanol. Let's see, that has hydrogens in it, right? And sure enough, they started sweeping their frequencies, and a nice signal came out. They said, oh, great. We're getting a signal there from this ethanol sample. And then they kept sweeping the frequency down here, and they got another signal. And I thought, oh no, what? Did you just put the one thing in there for hydrogen? Yeah, why are we getting two signals? And then they kept sweeping the frequencies on down, and they got another, even bigger signal. And they thought, wow, we've got 3 signals? What's up with that? How are we getting 3 coming out of this? This is ethanol after all. Well, they decided, well, maybe our RF signal's a little off, maybe it's not tuned quite right, or maybe the detector's off, and they had to play around with it quite a bit. And these are radio frequencies, by the way, and the detector is a radio frequency detector. And the legend goes they could actually listen to the AM radio while they were building these primitive devices. They could hook up a speaker and listen to the music at the same time. But no, they worked on the instrument and got it to behave better, get better resolution, and these blobby-looking signals, which were their original things, were really poor. They got a bigger magnet, and they got some better electronics. And what they saw, they put the sample again in. They still got this nice broad thing right about here. And then this other one here, amazingly, split into a 4-line pattern. It looked like a quartet. This one was staying as a singlet. Okay? So this is this multiplicity thing I like to get into right away, talking about the historical thing. And in fact, they could take the area under these 2 signals. They actually cut out these peaks here and actually weighed them on a balance to get the area in the first time. And the ratio turned out to be 2 to 1. The area under this signal was twice that one. Well, they kept sweeping down here, and they said, well, what about this crazy signal? Well, it turned out to be not a quartet, but a triplet. Wow, that's an amazing thing. And integrating this, it turned out to be 3. Okay? So at this point, the physicists were saying, well, this is really crazy stuff. I put in a sample that has the one nuclei I'm interested in, but all of a sudden it's got 3 signals, but it's got this hyperfine splitting pattern to those signals. And the physicists, this was just kind of an annoyance to them. But they shared this data with some chemists in the chemistry department, and the organic guys went, wow, there must be something about this. We can say that these 3 hydrogens here are different than these 2 here, and different than that one there. And that corresponds to the 1 to 2 to 3 pattern, right? You can kind of see that already. Let's look at this. Well, this is a singlet here and it's broad. Well, that's the one on an OH group that can be hydrogen bonding. It'll be broadened out, the different states of that molecule in the condensed phase. And there's no splitting there. A lot of the time it's not localized on this oxygen, so it's not split by these neighbors here. But on the carbon framework, the splitting sharpened right up, and that detail became very important. We said, okay, this guy's a quartet, and it's worth 2. This is the one worth 2. So if you look at these 2 hydrogens here, that's the integration. And how many neighbors does it have? Well, it has 3 neighbors. And so by the n plus 1 rule, n would be 3 plus 1, it shows up, yeah, it's a quartet. Okay, which is really cool. And then the other one here, this one here, which integrates for the 3, that's when we're observing these 3 here. How many neighbors do we have? The 2 neighbors. And so 2 plus 1 winds up being what, a triplet for that. Isaac, do you have a question?
You said the protons in the middle have 3 neighbors. Wouldn't they have 4 with the hydrogen on the oxygen there?
Right. So that's the thing about having those exchangeable hydrogen bonded groups, if it's on an alcohol or an amine that's next door. Because of hydrogen bonding, it's not localized to the same extent there. If you actually dry the molecule carefully, and especially if it's a secondary alcohol under idealized conditions, sometimes we can see splitting to an alcohol. But under normal conditions, where it's not very pure, and trace amounts of water and acid can actually make that hydrogen bonding more extensive, and we see even less of it. And this tends to be broad, and we don't see the splitting there. But very good question. We'll get back and see some examples of that. And that gives you a little historical perspective here. The crazy grad student from the Harvard physics department went over to the stockroom and they gave him ethanol. And sure enough, singlet, quartet, triplet, we'll need to define these ppm values or the delta values, and you'll see that coming up. But these absorbances and the 3 different signals, 3 different signs or signals are the distinct sets there. So let's go back here and see what type of sets or how many we expect for different molecules. And let's take some time here to determine how many signals or how many non-equivalent sets we might have. What would we expect to see in the NMR before we go back and do a lot of interpretation here. So let's look at this molecule, which is just what? Dimethyl ether. And you'd say these 2 methyl groups are the same. We have a symmetry element here. And anytime we have a symmetry element, either a mirror or a rotational symmetry that exchange the 2 groups, we say that those are the same set. So we'll expect 1 set of non-equivalent hydrogens, so we'd only see the 1 signal, okay? And there's actually no hydrogens on the adjacent atom here, so it'll show up as a singlet. But let's not worry about that yet. Just how many sets do we expect? How about ethyl chloride? How many sets of non-equivalent hydrogens will we expect to see in the NMR? Well, this methyl, CH3, is different than the methylene, okay? In proximity to the chloride, and there's no symmetry exchanging those 2 groups. So how many sets? 2 sets, okay? Expect to see that in the NMR. How about this ether? How about ethyl methyl ether? So this methyl is different than that methyl, even though they're both CH3s. This one's directly attached to oxygen. This one has a methylene in between. And there's no symmetry to exchange that methyl and that methyl. And then this methylene's distinct. So how many sets here? Right, 3 sets, okay? How about this ester here? So this is ethyl propionate. How many non-equivalent sets, or how many signals do we expect to see in the NMR? Again, this methyl on the end is different than that methyl because they're in different locations relative to the carbonyl and the alkoxy oxygen. So that's a set. This is also a set. That's different. This is alpha to the carbonyl. This methylene is alpha to that oxygen. So that's different also. So how many total sets? Right? 4. So that's very different. How about this one? Yeah, you have to be careful here. This is where things get a little bit tricky. You could say, well, we got one set here. These are the same, 2. These are the same, 3 and 4. Okay, maybe. But let's look at what? The old chair guy rears its ugly head again, right? Conformational analysis. Now, at high enough temperatures, these may all exchange, and you may just see the 4 sets. But if we cool this down temperature-wise, and you can cool down the whole probe inside of the NMR, we put the bigger group, the bigger atom, what the chloride here, equatorial. And so this hydrogen here, alpha, is certainly one set that's distinct. And then we've got this near plane symmetry right down the middle of the molecule. These 2 are a different set. But notice this one and this one are different than that one. These 2 are what? Trans to the chloride. These 2 that are axial here at this position are what? Cis to that chloride. So that we're already up to 1, 2, 3 sets, right? And then this one, that's a 4th set. And then this equatorial here is actually a 5th set. And then what about this one? This one's trans to the chloride, and this one's cis to the chloride. So how many total sets do we have here? Not 1, 2, 3, 4, but if we invoke the equatorial conformer here, we can see we've got what? 7 sets. Ouch. That's where it gets a little more complicated, doesn't it? Let's look at alkene compounds. So if we just have ethylene or ethene, we've got a lot of symmetry here, right? Mirror plane here. So how many total sets do we have? Just the 1. Okay? They'll all resonate at the same spot. But what if we have this? What if we have fluoroethylene? How many sets do we have now? Now this is different, right? This hydrogen's on the same carbon as the fluoride, so that's different than these 2. And what about that one versus that one? Now, if they're magnetically non-equivalent, if they're what? Geometrically non-equivalent, this fluorine is what? Cis to that hydrogen. This hydrogen here is trans to that fluoride. So do you think those 2 are the same? No, they're in different magnetic environments, different properties here. So how many sets do we have? 3. Okay, so that's, again, a little bit different. What about this one? Speaking of cyclic structures, 1,1 dimethyl cyclopentane. Are the methyls the same here? Yeah, we've got symmetry through the molecule here. What about this hydrogen and that hydrogen? Well, they're both, arrayed cis to a methyl. In fact, we have a mirror plane right through the middle of the molecule this way. So actually they're the same. And plus these over here are the same here. So actually we have 1 set here, we have another set there, and certainly these 4 are different than these 4 because of the proximity of the gem dimethyls. So how many total sets do we have here? Due to the gem dimethyl arrangement here and the extra symmetry, it's what? 3 sets. Okay. So hopefully that makes a little more sense there. Let's see, we can do some more examples of that or get into topicity. Maybe I'll delay that for next time. Let's see, maybe we'll end this, class time at that point. So far we've just looked at the basics of NMR. We've introduced you to the shift value, the delta value. Make sure you're reading ahead and looking at that. Focus on those 3 key events that we're talking about in NMR. We're talking about the shift, or the delta value, which tells you the kind of hydrogens in these non-equivalent sets. And then we're looking at what? The integration, how many hydrogens are in each of those sets. And then the 3rd key idea is the splitting pattern, the multiplicity, which tells us the neighbors. And that will tell us the proximity of where those different sets are arrayed. If we bring all 3 of those concepts together, we have a very powerful approach to determine the structure of these molecules. So practice some of these, and we'll do some more next time. and get more into the details of the shift value and of course the splitting. So we've got a couple more class periods on chapter 14. So very good. We'll see you next time. Thank you.